This is RS latch using two NOR gates. This is its De Morgan equivalent. This is RS latch using NAND gates, and this is its De Morgan equivalent. This is RS latch with clock signal. It is clocked latch. Truth table of clocked latch RS latch is shown in this table. When clock is 0, output Q is no change, and when clock is 1, then output Q is no change when R and S both are 0, and there is a race condition when R and S are equal to 1. So here the race condition is that clock and R and S, all these signals, if all these three signals are 1, then we have a race condition, and whatever output we can get. So we have to avoid this race condition. Next flip-flop is D-latch. D-latch is a new kind of flip-flop in which possibility of race condition is eliminated. First we look at unclocked D-latch. D is an input bit, and we are using here two NAND gate, or in place of two NAND gates we can use this circuit having two OR gates with inverted inputs. This is De Morgan equivalent. In place of using two NAND gates, we are using these two OR gates with inverted inputs. This is unclocked D-latch. Input signal data bit D goes directly to S signal of lower NAND gate, and D bar goes to R signal of upper NAND gate. D bar is obtained by using a NOT gate. This NOT gate followed by D will produce D bar, complement of D. So this figure shows a unclocked D latch. Because of the inverter, data bit D drives the S input of NAND latch. Data bit D drives as input of lower NAND gate, and the complement D bar drives the R input of upper NAND gate. A high D sets the latch Q equal to 1. If D is high, S is high, so it sets this latch and output Q will be high, that is 1. And if data bit D is low, that is 0, then input R, reset input, becomes 1 and this latch resets. Hence, output Q will be low, that is 0. So, if data bit is 1, then output Q is 1, and if data bit D is 0, then output Q will be 0. This table summarizes the operation of this D latch. When D is 0, output Q is 0. When D is 1, output Q is 1. The inverter guarantees that S and R will always be in opposite states. So it is impossible to set up a race condition in the D latch. Since S input is equal to D and R input is equal to D bar, so the race condition R equal to 1, S equal to 1 is not possible here. Next is clocked D latch. Level clocked D latch is shown in this figure. Now data bit D goes directly to upper NAND gate and its complement D bar goes to lower NAND gate using an inverter or NOT gate, and a clock signal is applied to the inputs of both NAND gates, and output of these two NAND gates are connected as shown in this figure. Level clocked D latch is shown in this figure. When clock is low, the latch is in inactive state and the circuit stores or remembers. When clock is high, D controls the output. A high D sets the latch while a low D resets the latch. Table D summarizes the operation. X represents a don't care condition. It stands X represents a don't care condition. It stands for either 0 or 1. This is the truth table for clocked D latch. If clock is 0, then whatever the input may be, either 0 or 1, output Q will be no change. And when clock is 1, then output Q is 0 if D is 0 and output Q is 1 when D is 1. So this input D controls the output only when the clock is high, and if clock is low, then the circuit remains inactive, no change. This figure shows the timing diagram for clocked D latch. Initially, we see that clock is low, D is low, and Q is low. Then we see that clock goes to high, D is 0, then Q is 0 again, and when D becomes 1, then Q becomes 1 because at this instant clock is high. Now clock goes to low and this D goes to low. D goes to low, but Q did not go to low. It is high because at this instant the clock voltage is 0. So output Q will change according to D only if clock is high, that is 1. When clock is low, the output cannot change no matter what D is. When clock is high, output equals input, that is Q equal to D. Figure E shows the timing diagram. When clock is low, the circuit is latched and the Q output cannot be changed. When clock is high, the output equals to input, Q equal to D. When D goes to high, Q goes to high, and when D goes to low, Q goes to low. The latch is transparent, meaning that the output follows the value of D while the clock is high. Now we see edge triggered D flip-flop. Edge triggered D flip-flop is a D flip-flop that samples the data bit at a unique instant. We see that clocked D latch. In clocked D latch, output Q will be equal to data bit D when clock signal is high. So for complete half cycle of clock signal where clock is high, output can be equal to the input D. In edge triggered D flip-flop, the data bit, it samples a data bit at a unique instant. This is the circuit of edge triggered D flip-flop, it is similar to that of clocked D flip-flop, except that we have inserted a RC circuit in front of clock. So clock signal is followed by a RC circuit. This figure shows a RC circuit at the input of a D flip-flop. Time constant RC of this RC circuit is taken much smaller than the pulse width of clock. Because of this, the capacitor can charge fully when clock goes high. When this clock goes high from low, we call this as rising edge. When clock goes from 0 to 1, it is called rising edge of the clock. And when clock goes from 1 to 0, we call it as falling edge of the clock. Or we can call these two edges as positive edge and negative edge. In positive edge or rising edge, clock signal goes from 0 to 1, and in falling edge or for negative edge, clock signal goes from 1 to 0. So we see that if time constant of this RC circuit is very small compared to this time period of this width of this clock signal, then this capacitor of RC circuit charge fully when this clock signal goes from 0 to 1 or when its rising edge comes. And then we see that voltage across R will be like as shown in this figure. And similarly, when this clock signal goes from 1 to 0, that is falling edge or negative edge, then we also observe a sharp edge like as shown in this figure for the voltage across the resistance. The diagram of voltage across the resistance of RC circuit is shown in this figure. Capacitor can charge fully when clock goes high from 0 to 1. This exponential charging produces a narrow positive voltage spike across the resistor. This is the positive narrow spike on left side, and there is negative narrow spike to the right side. Positive narrow spike to left side is when clock goes from 0 to 1 for its rising edge or positive edge, and on right side we have a narrow negative voltage spike for the voltage across the resistance of RC circuit. And now this clock signal, which was a square wave signal, now it is converted into this type of signal having positive and negative narrow spikes at the two edges of the clock. Later, the trailing edge of the clock pulse results in a narrow negative spike. The narrow positive spike enables the input gates for an instant. The narrow negative spike does nothing. At the unique time of positive spike, D and its complement hit the flip-flop, forcing Q to set or reset. So the output Q will be set or reset at a unique instant of time, and that unique instant of time is the positive spike. It is the time of positive spike. So at the unique time of positive spike, D and its complement hit the flip-flop inputs, forcing Q to set or reset. Output Q will be set if D is 1 and it is reset if D is 0. So output Q will be equal to input data D at the positive spike, at the unique time of positive spike. This kind of operation is called edge triggering because the flip-flop responds only when the clock is changing states. In figure A, triggering occurs on the positive going edge of the clock, so it is referred to as positive edge triggering. Figure B illustrates the action. The output changes Q equal to D only on the rising edge of the clock. So input data D is stored on the positive going edge. Table C summarizes the operation of the positive edge triggered D flip-flop. The up and down arrows represent the rising and falling edges of the clock. The last two entries indicate an output change on the positive edge of the clock. Look at the truth table. This is the truth table. When clock is 0, whatever D may be, output Q will be no change. When clock is 1, that is high, whatever D may be, output Q is no change. And if we have negative edge of this clock, then also whatever D may be, output Q will be no change. So output Q will respond according to input data D only when we have positive edge of this clock. Last two entries shows positive edge of the clock, and for this positive edge of the clock, when D is 0, Q is 0, and when D is 1, Q is 1. In this way, this edge triggered, positive edge triggered D flip-flop works. Difference between edge triggering and level clocking. There are two differences in edge triggering the output can change only on the rising or falling edge of the clock, while in level clocking the output can change while the clock is high or low. In the case of edge triggering, the output can change only at one instant during clock cycle, while in the case of level clocking, correct this. In the case of level clocking, the output changes during entire half cycle of the clock, either positive half cycle or negative half cycle. So correct this term, this sentence for level clocking. Here it is written that the output can change only at one instant during clock cycle. It is for edge triggering. For level clocking, the output can change for complete half cycle of clock signal, either it is positive half cycle or it is negative half cycle. Next, we can use preset and clear. This is the circuit diagram of edge triggered D flip-flop with preset and clear signals. For edge triggered D flip-flop, we use clock signal followed by RC circuit. This circuit using preset and clear is similar to this previous circuit, except that in between these gates we have inserted two AND gates, and output of upper NAND gate goes to input of upper AND gate, and output of lower NAND gate goes to input of lower AND gate, and preset is the input of upper AND gate and clear is the input of lower AND gate, and the remaining circuit is same. By using these two new signals, preset and clear, we see that a low preset forces Q to equal 1 and a low clear resets Q to 0. Table E summarizes the circuit action. When preset and clear are both low, we get a race condition. So preset and clear should be kept high when inactive. If preset is taken low, flip-flop sets Q equal to 1, and if clear is taken low, flip-flops resets Q is 0. If clear is 0, then we get output Q as 0, and if preset is taken low, if preset is 0, then Q is 1. This is the truth table for edge triggered D flip-flop with preset and clear. The first condition is in which preset is 0 and clear is 0. It is the race condition, so we have to avoid this. And when preset is 1, clear is 1, then for rising edge of the clock, output Q will be equal to D. And for low preset and high clear, output Q is 1. It is set with low preset. And when preset is 1 and clear is low, then output Q is 0. So it is clear, that is 0, output is 0 when clear is 0. This is the symbol of edge triggered D flip-flop with preset and clear. Figure F shows the symbol of a positive edge triggered D flip-flop. The bubbles indicate active low state. To preset the flip-flop, the preset input must go low temporarily and then return to high. Similarly, to reset the flip-flop, the clear input must go low temporarily and then be returned to high. This is the symbol for positive edge triggered D flip-flop. We have a input D, a clock signal, outputs Q and Q bar, and two inputs PR and CLR. PR is for preset and CLR is for clear. Two bubbles are formed for preset and clear. These bubbles indicate active low state. It means that it will be active when this signal is low. For example, the clear will be active when clear is low because this bubble is formed. It means then when clear is 0, preset is 1, then output Q will be low, that is clear. So output Q will be 0, that is clear, when this clear signal is 0. So this clear signal active when it is low due to this bubble sign. Similarly, the preset will be active when this preset signal is low. So when preset is low, clear is high, then output Q is high, that is 1. It is preset. Output Q is preset, that is 1, when this preset is 0 because it is active low.